So today I would like to tell you about a few aspects of impurity physics, or polaron physics if you wish, but in a very specific setup where the impurity has a charge. And this is not very unusual if you think about it, because I will refer to a specific realization in an ion-atom ultracold system, but in fact charged impurities are ubiquitous, and the original formulation of the problem dates back to 100 years ago, when Landau and Pekar were studying the generic problem of an electron just moving in a medium. So electron has a charge and it polarizes the medium, so it makes perfect sense to consider charged polarons. And I will not talk about electrons, but about ultracold atoms mixed with ions, realizing a different regime and leading to ionic polarons, or mesoscopic bound state formation. And then I will tell you a little bit about switching the environment from the bosonic system, as in the original ideas, to a Fermi gas. So yes, if you look back to the 1930s, Landau and Pekar wrote down a very simple theory for an impurity with some wave function having some kinetic energy, and due to its charge inducing a polarization in the medium, and this polarization interacts with the field of the impurity, so there is a contribution to the energy. If you try to minimize this energy, you get a nice nonlinear integral differential equation for the impurity wave function, in which it interacts due to the Coulomb interaction, but with itself, sort of. And here kappa is the medium-dependent constant. So this is hard to solve analytically, but one can think about studying the properties of this solution and maybe extracting the dispersion relation, and then after you have the dispersion relation, checking if this is still a quasi-particle with a well-defined effective mass. So this is a very old, very simple problem, but turns out it's surprisingly difficult to solve. And if you try to write a fully quantum version, like Friedrich did, you have an impurity, and then your environment can be, to a good approximation, a set of harmonic oscillators. And the simplest interaction you can write with these harmonic oscillators is just one creation or annihilation operator. So this is absolutely simplest thing you can write, and it turns out it is still bothering mathematical physicists to this day. If you try to think about putting a particle in a Bose gas, in a condensate, it quickly turns out that you need more terms. This is not sufficient, and the next order terms play a critical role. But you would typically replace this VQ by a contact interaction, which would be constant in momentum. And if you have a longer range interactions, not a contact one, you should consider varying this VQ and using some finite energy corrections, such as the effective range corrections, but maybe also the full dependence on the momentum. One example here is the Rydberg polaron, in which the Rydberg electron is interacting with the Bose gas, and you get a very rich spectrum with few body bound states and then a polaronic branch, studied, for example, by Richard Schmidt in theory. Then this theory at weak coupling can be solved perturbatively, and you recover a well-defined quasi-particle with a slightly increased effective mass due to the dragging of the impurity by the moving particle. But what happens at strong coupling, where things get non-perturbative, is less clear if this is still even a well-defined, if this effective mass still exists. And for example, Eddie Timmermans showed in a very nice paper that after you make some approximations, you can, at strong coupling, get a result where the wave function is localized, even though there is no disorder. There is a self-localization of the particle. The effective mass diverges, and you have just an immobile impurity. If you switch from bosons to fermions, you have the Chevy ansatz, which is the simplest variational solution. But for a long-range interacting system, this is less clear. And I will talk about our very simplistic approach to this problem in the second part of the talk. So I would like to focus on these long-range interacting systems, and the example that I have in mind is an ion, an atomic ion, which is very nicely routinely realized now in experiments, and we had a talk about that yesterday, that ions can be kept and very well controlled in radio frequency drops, which for my purpose is just a harmonic oscillator, and I will neglect any time-dependent effects. They can be laser cooled to the ground state, detected optically. You can also push the ion with electric fields and study the dynamics. If you happen to not have an RF trap, you can push the ion through the gas and then detect it with a multi-channel plate, which was done in Tilman Faust group. But in any case, what we want is that we have also a called atom setup, which is perfectly overlapped with this ion trap. So this is a realization from Tobias Schett's group in Freiburg, where they have these big coils forming the pole trap and a set of lasers forming the optical trap for the atoms. And in principle, you get a nice charged impurity in a gas. Here it's a Fermi gas, so that arrows represent the spins. If you now think what is the difference between a neutral case and the charged case, the potential depends on the fourth power of the distance between the atom and the ion, which is different from the van der Waals interaction, but this is just a change from 6 to 4 here. So one may think it's not a big change, but the typical length scale associated with this interaction is orders of magnitude larger than for cold atoms for neutral setups. And this in fact competes with the other length scales of the system, such as the healing length of the condensate. So you can no longer separate the lengths in your system, and using the pseudo potential becomes questionable. Moreover, due to this long range, the characteristic energy that you have to beat in order to get to the S-wave limit becomes sub-microkelvin. So it turns out it's pretty hard to cool the system down to this energy, because an ion in an RF trap tends to be a nasty creature to control at these energy scales. Yes, and in a typical experiment, you will have this competition between the condensate length scales and the interaction. And the bound state, the two-body bound state of an atom and an ion, has roughly this size. So it will also interfere with the condensate. And you can expect that probably few-body physics will be important, not only on the two-body level, but it's very easy to have more than 2 particles in the close vicinity. And the nice thing is that an ion has a hyperfine structure, so you can expect standard Feshbach resonance physics between ions and atoms, and you will be able to control the scattering length of this long-range potential and realize repulsive and attractive regimes. The only problem is how to observe these interactions, because you have just one ion, and also it's very hard to cool beyond this S-wave regime. But a good experimentalist can do it, is always my answer as a theoretician. And in fact, we found a good experimental team in Freiburg who were able to observe these resonances. As they scan magnetic fields, they measure the probability that they still have ion in the system after some interaction time. And if they lose the ion, it's probably because of some three-body event which gave the ion a lot of kinetic energy or created a molecular ion due to the recombination event. And they found this very nice peaks in the ion survival probability as a function of magnetic field, indicating the existence of Feshbach resonances in this system. So we are, or they are good enough to control the interaction, and so that in principle many-body physics can also be studied in this system. In the case that they were studying barium plus and lithium, we have some additional complexity. This Feshbach resonance spectrum is hard to characterize theoretically due to a large spin-orbit coupling in the potential, and possibly because of the external electromagnetic fields present in the setup inherently due to the pole trap. And we have to consider more than one partial wave in contrast to what is usually done in cold atoms. So it's a bit less convenient to work with than usually. But still, we confirm that this is a free body event, and also if you look at the two-body collision rate, it's also very increased as the resonance. So the ion, you can see that the ion thermalizes with the gas much faster where it's close to the resonance. So that's very nice. Now, what will happen in a many-body setup beyond the Feshbach resonance physics? So if you, as I told you before, we have a high chance that there will be lots of bosons in this attractive potential well close to the ion, but the bosons repel each other, so we cannot put infinitely many here, that the gas is not infinitely compressible. So the basic question is how many bosons can be bound to the ion in a typical setup. And if you do just mean field estimate, you get the answer that it's many thousands. So the problem is the standard polaron treatments, such as basing on a Gaussian ansatz or Bogolyubov theory, will probably fail to capture this because the density around the gas will increase, around the ion will increase a lot. And this will be a beyond mean field effect. At some point, these games become strongly correlated because the bosonic repulsion will be very large. So, we need a better treatment. And we want to keep this R to the 4 potential here, but also it diverges, so we need to regularize it for numerical calculations in some way. And here you can see the snapshots of the system for different number of particles coming from the Monte Carlo calculation done by Grisha Astraharczyk from Barcelona. If you have just 50 ions, they will all cluster around the ion. But if you have 500 already, there is this large density increase around, but some atoms form a background, so it is really some kind of maybe a quasi-particle moving in a background gas. And not all the atoms are close to the ion. So this mean field estimate is obviously too pessimistic. So we relied on Monte Carlo to tell us how many atoms cluster around and form this many-body bound state. And here is the result, the ground state energy of the system as a function of the number of particles. So first you throw bosons close to the ion and they all settle up in this ion atom bound state. So the energy falls down linearly with the number of particles. Every boson just settles down in this ground state, and the bosonic repulsion is too weak to matter. And at some point, there are enough bosons that the bosonic repulsion takes over, and you bend away from this curve. And at this point, you can say that the quasi-particle is, or this many-body bound state is saturated, and now as you add particles to the system, your energy doesn't change or changes very weakly. And this is just setting up this background gas. If there is no bound state in the atom-ion potential, this is an artificial assumption, but we can make it in numerics easily. This is not the case. There is no bound state to populate, so your energy just straight away increases. And this resembles very much the standard attractive polaron theory. We can also consider what happens if you have two ions pinned down in a Bose gas interacting with each other. One could ask what about Coulomb repulsion, and our answer is we just turn it off because we want to see what is the induced interaction just only due to the bosonic medium. And it turns out this induced interaction, so energy as a function of the separation between the ions, has some nice features. If the atom-ion interaction is very, very weak, this looks more or less, you could fit a Yukawa potential to that, and it would not be very far off. But as you go to stronger interactions and consider the impact of this two-body bound state, you get much larger energy scales, because now you just populate again this bound state energy, and you get a nice, interesting non-analytic feature in this effective interaction, which happens at the point where the density of atoms is maximal around the ion. So a single polaron would have this, more or less this size. Okay, you can also try to go beyond the ground state, and now we cannot do Monte Carlo anymore, but you can try to check if some kind of a simpler approach would work. So we drew from an old work by Gross from the 60s, who suggested to move to the co-moving frame with a Lillo-Pines transformation and do the mean field in this frame. And if you do that, you get a very nice, very simple energy functional for the reduced wave function. You can minimize it, and you get a stabilization of the system due to screening. So bosonic repulsion screens the bosons from collapsing all close to the ion. And if you compare the bare interaction and this effective interaction, you can see that it's much more shallow, and you get an increase of the density around the ion, but not a dramatic one. So this mean field-like ansatz, while it's very far off in the Manybody bound state regime, it gives you reasonable answers if you're in a weakly interacting regime. Now, what if you switch to the Fermi gas? Well, we wanted to set up a simplistic model that takes into account the strong density increase of the fermions around the impurity, while still being on a reasonable level where we are able to give some analytic answers. So we assume that there is a d-dimensional Fermi gas in a box attractively interacting with some mobile impurity. And there are a lot of fermions, so the Fermi C is far above the zero energy, and all the impurity fermion bound states are populated. And the simplest local density approximation gives you a reasonable Hamiltonian with the impurity, just the Fermi gas and the interaction between them. And we can try to minimize it. So you minimize over the Fermi gas density, you get an answer which depends on the convolution of the potential with the impurity density profile. Now you can make the approximation that you have positive chemical potential everywhere, so you have a lot of fermions everywhere. And then you can invert this relation to get the chemical potential, which in 2 dimensions is nice because 2 over 2 is 1, so this gives you an easy formula and a very simple result for the impurity energy functional, which very much resembles the Pekar functional from the first slide. There is an impurity kinetic energy, a self-interaction induced by the medium, where this is the convolution of the impurity atom potential with itself. And it is a bit different than the Pekar functional. These are fermions after all. And you can try to minimize it. We just did it analytically on a Gaussian potential and with Gaussian wave functions to see what is happening, just to give us a flavor of the physics. And we just minimize the energy with the width of the Gaussian, so the impurity wave function. But already what we get is interesting because we get self-localization at the critical interaction strength. You can see that for a weak potential, the energy depends on the Gaussian width in a monotonic way, but for a larger potential strength, you get a different behavior. And both in 2D and in 3D, we get the effective mass, which first increases, but then drops. So the inverse drops to 0, which means that the effective mass diverges. So within our approximations, which are probably not fully right for this problem at strong coupling, we get the self-localization phenomenon. And the effective mass here was extracted using an idea borrowed from Robert Zeiringer. Okay, so in conclusion, I hope I convinced you that ion atom systems are now in the quantum regime, controllable enough to study Manybody physics, hopefully soon in experiments. And this problem is a bit exotic in that it has competing length scales and energy scales, which leads to strong correlations in the gas. And long-range interactions are interesting, and within a simple theory, they lead to a self-localization. So these are some papers. Some of them will be submitted hopefully this summer, in particular the last one. And this is my group. My student João is here and has a poster, so we still have half of a coffee break if you want to see him on a very different project. And Piotr also has a poster on a very different project. Thank you.
Thank you for the exciting talk, and now time for questions. In the back, too.
Thank you for that nice talk. What's the role of inelastic three-body processes if you have this system. I mean, how experimentally realistic are these states that you are calculating?
Well, to some degree, it's similar to neutral atom setups in which three-body collisions destroy the polaron after some time. So it has a finite lifetime, and you have to find a sweet spot to mitigate this loss process. On the other hand, three-body collisions also contribute to formation of this polaron. So there will be a finite extent in the dynamics where you throw the ion into the gas, where there will be a buildup of correlations around it, also due to three-body processes, and then you will form a molecule, and probably the process will be over. So our description will no longer be valid. But that's also the case in other polaron physics in cold gases.
So what's the condition for the sweet spots? I mean, what do you have hope?
Yeah, I still do, yes. And experimentalists like Tobias Schatz also has hope. So we agreed to try to see an increase in the effective mass on a moderate timescale, and they think it should be possible.
Okay, thanks.
Any more questions?
Thank you for the interesting talk. Can you commented that you had to move to a co-rotating frame in order to be able to apply mean field?
Yes, I moved to the co-moving frame. This is a standard, in a way, a standard technique back from the 60s, because in general this Hamiltonian is you can try to minimize it, but you can also remove the impurity degrees of freedom by moving to this co-moving frame. Where am I? Yeah, so you make use of the conservation of momentum in a way, and then your transformed Hamiltonian, I didn't put it here, but it simplifies quite a lot because you get rid of all the impurity coordinates at the cost that you have a correlated term which has a sum of all the atomic momenta squared. And then if you assume that your system is spherically symmetric and the total momentum is 0, this term can be disregarded. And you get effectively just a gas in an external potential, which is the impurity boson potential. So that is, to a good approximation, you can think about it as just a gas in an external trap due to the impurity.
I see. Okay, thanks.
Any more questions or comments? If not, thank you very much.